Okay, we are now on lecture 12, talking about Jovian planetary systems. This is subtly italic because the idea is that it's not just the planet that's important or interesting. Where we are in this section is we're taking this tour, starting at the terrestrial planets and just working our way out, and we're now here. Collectively, Jupiter, Saturn, Uranus, and Neptune are called the Jovian planets, and we'll talk about them as a group because they actually share a lot of similarities in structure. And of course, remember, this picture is absolutely a cartoon and totally not to scale like anything is in astronomy. Okay, so the key points that we're going to talk about is that Jovian planets are considered to be systems. They consist of the planet itself, a large collection of moons, and rings. They actually all have rings, even though Saturn is notorious for his or her. The planets themselves, we'll talk about the composition of the planets, and then the Jovian planetary weather, which is actually very remarkable. Of the moons, we'll talk about the fact that there are lots of them, so that's generic. And some actually have some analogs to terrestrial planets. So the idea of them being alive or dead and having some interesting geology is something that we'll discuss. And the rings, just realize they all have them, and then we'll show you some pictures. They look really neat, so we'll definitely bring that up. But I won't ask you guys about shepherd moons or gap moons or anything like that. Just enjoy it. Okay, so the first part of the system is the planet itself. So obviously the most conspicuous part of the Jovian planetary system. And the first thing to remark upon is that they're big. They're relatively big. So again, distances not to scale, but the sizes have been scaled appropriately. And you can fit about 10 Earths across the face of Jupiter. And these things are large and menacing compared to the little terrestrial planets down there. However, they're actually really fluffy. So despite their imposing size, they actually are relatively low density. So despite the fact that Jupiter is about 320, 318 times the mass of Earth, you could actually fit like 1,300 or so Earths inside of it if Earths were marbles and you had a Jupiter-sized jar. So the reason for that turns out to be because they're mostly gas. I mean, the alternate name for these planets are the gas giants. But just realize how low density they are is that Uranus is about the same density as pencil lead. And if you were to put Saturn in a really large bathtub, Saturn would float. So the density of water is 1 gram per centimeter cubed by definition almost. And Saturn is 0.71 grams per centimeter cubed, so 71% of the density of water. So that's about the density of pure grain alcohol. So these are really, really, really fluffy planets. And the reason for that, again, is that they're mostly composed of hydrogen and helium. So that's not good enough for us in this course. So what we're going to do is we're going to cut them in half and look at what types of hydrogen and helium they're made out of, because that's actually turns out to be a pretty interesting story. And roughly speaking, Jupiter, Saturn, and Uranus and Neptune they're slightly different in composition, and we'll mostly focus on Jupiter and Saturn, partly because we know more about them. But if you cut Jupiter in half, what you get is these layers of visible clouds. They're hundreds of kilometers thick. And what they are a collection of things called volatiles. And this has a very specific meaning in astronomy, and you'll hear it a lot from this point out, actually, especially the people who do planetary science. It's a really important concept. So volatiles have nothing to do with being flammable or dangerous. What a volatile means from a practical standpoint is that they could be liquid, solid, or gaseous at normal kind of solar system temperatures. And we definitely are familiar with water being liquid, solid, and gaseous on Earth. So that would be ice, clouds, and the oceans. But in the temperatures and pressures that the gas giants or Jovian planets exhibit, you can actually do that with methane and ammonia too. So that means that you can have methane clouds and ammonia clouds, and you can have methane ices and ammonia ices. You could climb up a waterfall of frozen ammonia on the moons of Saturn if you really felt like it and had a large enough budget. But you'll hear this more and more. So volatile just means the state of the matter itself can change in between solid, liquid, and gas. So Neptune and Uranus and Jupiter and Saturn have lots and lots of volatiles. In the case of Jupiter and Saturn, these are mostly in their cloud layers. And in the case of Uranus and Neptune a little bit more closer to the center of the planet. So this will be a generic story further from the sun, so you can't really evaporate stuff as you get farther from the sun, so you tend to get more of it. And as well as that, there's actually gaseous, just straight hydrogen and helium as well. And the reason those exist on these larger planets is because they have more mass, so they have more gravitational pull, and they can trap lighter gases. You know what happens to a helium balloon on Earth? Well, if you have 318 times the mass of Earth, maybe that helium balloon doesn't escape. Okay, so this is Jupiter, and we'll use this as a template just to get a rough sense of what an inhospitable environment these planets are. So this would be a little sliver of a cross-section of Jupiter, and this would be a little sliver of a cross-section of Earth for comparison, about 1/10 of the size. And this is actually, nothing's to scale, but this isn't to scale. The Earth's atmosphere is very, very, very thin in comparison to the crust. So this should really be half of a pixel across. They did their best. And we've got atmosphere, crust, mantle, and core. And this is the same equivalent picture for Jupiter. And what you see is there's clouds and cloud layers and gaseous hydrogen, and this would be hundreds of kilometers thick, so hundreds of kilometers, and very, very, very puffy. So remember, water itself is 1 gram per centimeter cubed. So this is 2 10,000ths of that. And this is also something to keep track of, and really interesting, is this is the pressure that you would feel. So basically the force of all of the gas that would be bearing down on you if you were to take a really ill-advised trip into the center of Jupiter. And what 1 bar is that's basically what you feel on Earth. So if you go scuba diving and you go down 10 meters, you'll feel 2 bars, and you'll see a balloon that you take with you actually compress in half, so it'll be half the volume. And the limits of highly trained, highly paid saturation divers, they get down to about 20 bars. So that's really the limit of a human being. And you can see as you get to what's still what might be considered to be the edge or the clouds of Jupiter, you've gotten up to 50 to 100,000 bars, so 100,000 times the pressure of Earth. So that's no good, and you definitely shouldn't drop into the center of Jupiter without some protective equipment. So at some point, the gas, mostly hydrogen, helium again, the gas gets compressed so much that it actually changes phase and becomes hydrogen. So you get a layer of liquid hydrogen clouds. The temperature at this point, because of all the molecules banging around, has raised to about 2,000 degrees Kelvin, and about 500,000 times the pressure that you would experience on Earth. And as you go further still through this layer of liquid hydrogen, you actually get to something called metallic hydrogen, which turns out to be really important because the question, it might be forming in the back of your mind, or you may have yelled it at the computer screen already, is how do you know this stuff, right? So you've already described the fact that a human or a probe, no matter what you build, would be absolutely crushed on a trip into a gas giant planet. So how are you telling me that there's metallic hydrogen in the center? So the answer to that is, first we're going to talk about what metallic hydrogen is. And what metallic hydrogen is hydrogen that's been compressed so much that the electrons don't know whose proton they belong to. So if you remember what a hydrogen atom looks like, it's the simplest atom out there. It's just 1 proton and 1 electron. These things have been compressed so much that the electrons are so close together and the protons are so close together that the electrons really don't know which nucleus they're orbiting, and they're free to move wherever they want. So metallic hydrogen doesn't mean that there's a bar of it and it's shiny and, you can exchange it for goods and services. What it really means is that it has metal-like properties. So for instance, metals are really good at conducting electricity, and at these incredible pressures, the hydrogen is good at conducting electricity. If you were to put a battery, with 2 terminals there and there, you would get a large flow of current. And this is how we know the metallic hydrogen is there, because Jupiter has a very observable consequence of all of this incredible amount of metallic hydrogen. Okay, and then finally, presuming you made it this far, which would be a really big presumption, at the center of Jupiter, you get to what's sort of a Bermuda Triangle of captured comets. So this core of rocks and metals and probably other hydrogen compounds, hydrogen all the way down, that is nestled in the center. And there's definitely evidence that Jupiter has captured comets, and that's where they would go. Okay. So these planets are all very large and they rotate, and it turns out that big things are harder to stop, so they actually all have very short days compared to Earth. So this is a much larger planet, 10 times the diameter of Earth, but it's also spinning at about half the Earth day. So the day on Jupiter is about 10 hours, likewise on Saturn. The outer gas giants, or Jovian planets, 17 and 16 hours respectively. They're spinning really fast. And the idea behind that is that so our day has actually slowed down because the moon has stopped us through tidal forces. The day of Mercury has slowed down because the tidal forces from the sun. The day on Venus has actually not only slowed down, but almost stopped, probably because it was hit by something very hard. And it's got much less mass than Jupiter. So Jupiter, when it gets impacted by comets and asteroids, those aren't going to stop it. It's just that much bigger. Okay, so I've got a giant core of conducting metallic hydrogen, and I have a 10-hour rotation period. So my question to you guys is, what else do you think that these planets have? And is it large or small? So if you guessed that the outer planets, the Jovian planets, have magnetospheres, you're absolutely correct. So the reason we know this metallic hydrogen is there is it's got a consequence, and that consequence is an incredible magnetosphere. So the high rate of rotation of Jupiter and the fact that it's made of conducting material for the most part means that it has an incredibly big magnetic field. And this is the size of the sun for scale, and you can see that Jupiter's magnetic field, or the part that it actually shields, is shielding it from the incoming solar wind, is multiple sun diameters across. So this is an incredibly big magnetic field. And then likewise Saturn and Uranus and Neptune, they all have some metallic hydrogen and high rates of rotation. So really, really big magnetic fields, which is good because they have a lot of hydrogen and helium to protect from that solar wind. So this is a pretty recent flyby, if you didn't like my hand-waving argument. This is actually a picture of the aurora, probably borealis and australis. I don't know if this is flipped or not. But these are images, ultraviolet images, of the northern and southern lights on Jupiter from the New Horizons spacecraft when it did its flyby in 2007. So these are aurora borealis that you could fit about 3 Earths across, so really impressive. And this is capturing and shuffling that solar wind to the northern and southern poles, so really cool. Okay, so the weather on the gas giants, notably Jupiter, is also significant. Famously, there's the Great Red Spot. So the first person to look at Jupiter with a telescope powerful enough to see the Great Red Spot saw the Great Red Spot. So at least this thing has been on there for 300 years. And what it is it's basically an anti-hurricane, which sounds pretty cool, so talk about what that is. So if you've followed a tropical storm to a hurricane and, really tuned into the Weather Channel for that whole process, what you notice is that people start worrying about hurricanes on Earth with low pressure areas. So they say there's a tropical depression, which means there's a region of lower pressure. And what happens is air falls into that region of lower pressure, and due to a consequence of the Earth spinning is the low pressure zones start spinning as well. So you can think about it as the circulation in a flush toilet or a sink that's draining. You'll see things as it goes down, it'll start spinning, and kind of famously the toilet's supposed to go the other way in the southern hemisphere. I don't know if that's actually true. But that's a low pressure zone. So the drain in the toilet or the sink has less pressure than the water around it. So the same thing would happen if you took a hose and you held it up in the air. So if you were in the northern hemisphere and you took a hose, and it was a really powerful hose, and you had a high pressure zone as well as the water from the hose spraying out, it would actually circulate a little bit because of the rotation of Earth. So this isn't a sink or a drain. The reason we call it an anti-hurricane is because it's a high pressure area. So there's something that's been welling up and is now being spun out into this anticyclone because of the fast rotation of Jupiter. And it's been doing it for 300 years. So not a day goes by where this thing isn't raging on. So it's fairly incredible weather. There's really no conception of anything like this on planet Earth. So you can take an Earth and fit it there and there. So when people say anti-hurricane, you can now, just roughly speaking, it's a source, not a sink. So there's material welling up from the center of the planet. Okay. This is the really famous one, but there's actually been weather like this observed on all of the other Jovian planets. So famously, Voyager 2 saw something called the Great Dark Spot on Neptune. I know it's a really uncreative names again. So this thing actually is a transient feature. It's not there now. So it's a storm that actually was only seen for a few years, and it broke out on what would be considered to be the spring of Neptune's spring, so the 20 years that correspond to when it's starting to tilt towards the sun. Okay. So the next obvious feature or question to ask about these planets is, why are they colored in the way they are? And this has to do with these volatiles as well. Again, a volatile is something that can be liquid, solid, or gaseous, depending on the temperature and the pressure. And the one we're really familiar with is water. You can have solid water in the ice caps, and then liquid water in the ocean, and gaseous water in clouds. And you get clouds when water evaporates. Well, the temperatures and pressure gradients on these planets, the ranges over which you see temperature and pressure, are so high, you saw that a couple of slides back, that you can actually get ammonia going from solid to gas, or solid to liquid to gas, and ammonium hydrosulfite and methane, and all of these so-called volatiles actually make their own color of cloud, and they do so at a different height above the, if you want to call it a surface of the planet, then so be it. We'll just say at different heights. So if you see a blue cloud, that's methane. If you see this kind of tan-colored cloud, that's actually an ammonium cloud. The brown-colored clouds got nothing to do with dust or dirt. That's ammonium hydrosulfite. And so what you're seeing here, and it looks flat because we're so far away, is these cloud layers are actually separated by hundreds of kilometers, and each one's color tells you the composition. So primarily what you see on Uranus and Neptune are water, ammonia, and methane, and on Saturn and Jupiter you tend to see more ammonia and the darker ammonium hydrosulfite. So these are actually wildly separated cloud layers, so hundreds of kilometers. So that's halfway across the state. So you'd be seeing these clouds so high above you if you were fortunate or unfortunate enough to be picnicking on one of these planets. Okay, so the next question is, well, that's really cool, but they don't really look like clouds. They look like these crazy stripes with these kind of patterns in them. So what's going on with that? Well, the reason for that is, again, this is a very large planet, and it's orbiting very quickly. So the day on Jupiter is a 10-hour day. And so as this thing spins, what happens is warmer gas rises, same thing that happens on Earth. Hot air rises, in this case hot ammonium hydrosulfite rises. And as it rises, it actually gets whipped around by the very fast rotation rate. So the winds, because of the fast rotation rate on Jupiter, for instance, are over 400 kilometers per hour. So that would be like riding in a jumbo jet with the top down. And as a consequence, as they rise up, they get whipped all over the way around the planet into these stripe-looking bands. And the kind of fish-scaly patterns that you see here are turbulence, where it gets kind of chopped up by turbulence. So this story is verified by, and we'll ease into this. We'll have a full lecture on what different parts of the electromagnetic spectrum tell you. But we'll kind of start showing you more and more infrared images and read them the way that you just kind of feel like reading them naturally, is that this is hotter and this is cooler. So this is hot gas that's rising and being whipped around the planet. Here there seems to be some hot gas rising and being whipped around the planet around the Great Red Spot. And then finally, this is an animation of a couple of days on Jupiter, just so you tend to get these static images, but realize that these are dynamic and alive. So the weather patterns on these planets are constantly changing, and it's hard to tell from just a picture. And the fact that this has been persisting for hundreds of years. So you can see these smaller cyclones going around, and you can see the scalloping and the turbulence. And those balls that you see coming by are actually the moons of Jupiter. So these are real images. This is, I think, a simulation. Or they just fixed it so that the Great Red Spot is constant. Okay. So the next part of the Jovian planetary system are the moons. Many, many. And these are not all of them. I think Saturn at this point has 60 named moons. So obviously that's not all of them. But just to put them in perspective, these are some the moons of Neptune, Uranus, Saturn, Jupiter, at least representative ones. And these are Mercury, the Moon, and Pluto for relative scale. Okay, so the Moon is about the size of Io and Europa. Ganymede and Callisto, the two largest Jovian moons, are bigger, about the size of Mercury, but nothing's like terribly out of scale. So these are almost moon-like moons for the largest ones, and then much smaller for the smaller ones. So my question to you, and these have been included for a reason, is do you think that these are all geologically alive or dead or some mixture of the two? There's definitely something kind of funny going on with Triton and Titan, and why? So, I'm not going to put words in anybody's mouth, but since there's nobody here, is that if you just went off the logic that we used when we talked about terrestrial planets, is that smaller terrestrial planets are geologically dead because they cooled off faster. So if you presume that these were all formed at the same time, 4.5 or 5 billion years ago, and you would imagine that all of these objects are geologically dead. But it turns out that that's not true. And the rule of thumb actually flips, because terrestrial planets like Mercury and the Moon, not so much Pluto, Pluto has a completely different composition, is that these are made of rock and metal. So these are closer to the sun, and they're rock and metal, and as you get farther and farther away from the sun, you actually become comprised of more and more volatiles. And volatiles in rock melt and thaw at different rates. So the idea of the rock geology argument that we applied to Mercury and the Moon about them cooling off and they're really hard to heat up again, therefore they're geologically dead, actually don't apply, and something kind of funny happens where these flip. And you'll see the pattern in a second. So it turns out that Io and Europa, for instance, kind of act like they're geologically alive. They have things that would resemble volcanism and tectonic activity, and Ganymede and Callisto are a little bit more geologically dead. So that almost seems backwards, because Io and Europa, the geologically alive Jovian moons, are smaller. So what's going on with that? Well, first let's look at Io. So Io is absolutely riddled with what you would call volcanic activity. So this is about the size of Washington State for comparison. And all of these dark patches are where types of volcanoes, we'll just call them volcanoes for now, have gone off. And if you look really closely, you see this characteristic kind of hexagon basalt pattern. If you've been to Devil's Tower or the Giant's Walkway or any of these volcanic formations where lava dries, they tend to crack in these hexagons. So it's really smoke and gun volcanic activity, not like you really need it. And sulfur dioxide is stuff that comes out of volcanoes. It's actually kind of a greenhouse cooling gas. And so there's sulfur dioxide jets and sulfur dioxide frost. If that indirect evidence of volcanic activity wasn't enough for you, well, here's an infrared image, and you can just see these hot spots all over Io. That's the face facing the sun. And if that's not good enough for you and you really just want a picture, remember this is about 500 kilometers. So if you want to see a volcanic plume that's 100 kilometers tall, there it is. So Io is definitely spraying some incredible volcanoes. So this is able to go so high because of the really low gravity on Io. So it was amazing and terrifying. So why is this? What's happening? If this were a terrestrial moon, it would totally be geologically dead. So we would not expect to see volcanic activity. So it turns out that the tidal forces of Jupiter are the culprit. And it's not necessarily the tides that we consider that have stopped the moon due to its rotation. It's actually the tides that are caused by the fact that Io is in a slightly elliptical orbit. So Io gets closer and farther away, a little bit. But that's enough, because when it's closer, Jupiter will stretch it more, bigger tidal forces, because it's closer. And as it gets farther away, Jupiter will stretch it less, because the tidal forces will lessen. So essentially what's happening is Jupiter is playing Io like an accordion. And as it does so, all of the ices and rocks and volatiles and material in Io is actually being rubbed up against each other, and it experiences frictional or tidal heating, is how people describe it. So this thing is getting squished and pulled and squished and pulled and squished and pulled, and that actually is the source of heat that keeps it geologically alive and has a liquid core. So tidal forces. Europa, same thing. So Europa seems to have doesn't seem to have, it has these tracks all across it, and if you look very closely at them, they actually correspond to what you would see in the Antarctic or the Arctic when the ice sheets form, and you have two ice sheets come together, and they make what's called a pressure ridge. So these sheets will grind up against each other and form these parallel tracks where the ices bash into each other, and it's kind of like the tectonic plates that form mountains. It's just the ice version of that. So we actually have ice tectonics that you see on Europa. So why do you have this? The only reason that you have this is that it must be riding on a surface of liquid. So the current picture of Io and Europa, and there's some secondary evidence based on how it rotates that supports this, is that Europa has a magnetic core of very deep ocean, so hundreds of kilometers, and then riding on top of it is an icy covering made out of plates that can grind and interact with each other. So if you wanted to find, by far, it's a pretty good movie as far as its depiction of science and scientists, I gotta say. If you wanted to find extraterrestrial life, probably the best place to look is Europa. The Europa has a liquid ocean, it has chemical enrichment, and it has a source of energy in the sense that it's experiencing this tidal heating from Jupiter. So maybe there's life there. And people have actually made some serious proposals for autonomous submarines that make it through that. Okay. And then, somewhat paradoxically, the larger of the two so-called Galilean moons, Ganymede and Callisto, these actually look like geologically dead planets. Not 100%, but they're covered in craters, which means that their surfaces haven't been repaved by volcanism or ice tectonic activity for a very long time. So these are kind of what people may have expected. And I will say that people were kind of surprised by this, is that everything's obvious in retrospect, but the idea that Io and Europa would have these fantastic properties, people really didn't appreciate until the Voyager probes flew by. So we'll keep moving. This is an interesting one. If you wanted to go to one of Saturn's moons, and this is a subset of the 60 of them, which one do you think would be the most interesting to go to? I imagine everybody said Titan, and it's true. So NASA actually proposed a mission to go to Titan, and the way that these things work is you got to sell people on the mission. So you've got to come out, you find the craziest person on DeviantArt, and then you make them paint you this picture, and this picture shows these lakes and then these fantastic geological structures with Saturn in the background, and the probe's going to detach and go measure some stuff. Crazy, right? Okay, so this is the actual picture of the probe that was subsequently funded and sent, and these are these fantastic geological features. They're not rock at all, because the story of the Jovian moons isn't rock geology, it's ice geology. So this is like water ice, but it's water ice that will never thaw and may as well be rock for all intents and purposes. And Titan actually has this very, very jagged, sculpted landscape in places. The probe, the Huygens probe that landed, actually landed on a flatter area, so it landed on the beach. And this is a hydrocarbon sand beach near a methane lake. So there are lakes of liquid methane, not liquid water. Way too cold for that. But methane still remains liquid. So this is a twisted fantasy world of kind of frozen oil beach, frozen hydrocarbon beach by an icy set of mountains by a methane lake. And the environment is so inhospitable that the Huygens probe really only lasted for a short amount of time. It didn't collect data for a year. I think it was closer to a day, if not just hours, in 2005. But the images that it returned are pretty incredible, I think. It's on par with the artist's conception. And Titan definitely has a thick atmosphere. You can see the haze around it. So Titan has an appreciable amount of atmosphere. So actually, the Saturn's medium moons are kind of what you might expect, again, based on the terrestrial rule of thumb, is that these things look like traditional moons. They're cratered, which means that they haven't been repaved. They look very geologically dead. These kind of hermetic seal-looking things actually come from the planet cooling down so much that it shrinks and creates these kind of inverse stretch marks. I will just say that Mimas is sometimes colloquially called the Death Star for obvious reasons. But even that doesn't quite work. And it turns out that Enceladus, the whole moon itself, is about the size of Washington State, actually has these weird sort of tiger stripes on it. And even though you see cratering, you also see these what turn out to be very thin ice sheets. And there's a tail of vaporizing material coming off of Enceladus. So this is one of the smallest of the moons of Saturn that I showed you guys. So what's going on with that? And this is actually very baffling for people because now there are no rules. Is it the bigger planets that are geologically alive or the smaller ones or ones that are very small but not too small and not too big? It turns out that the current theory is that Enceladus is just in a lucky spot. And basically, again, the Jovian planets have very large magnetic fields, magnetospheres, because they rotate really fast and they have condensed cores where there's stuff that's squished so much it's conductive, is that Enceladus is just in the magnetic field of Saturn, and it's kind of getting lit up by the plasma material that's being blown off of it. And this is what's causing it to grow this little tail. So, okay, I'll just throw the rest up and we'll, just look at some pretty pictures, and you should see some of this terminology because it really is indicative that there's a lot more stuff to study. So these are the Uranian moons, and if you look at the smallest one, Miranda, again, it's about the size of Enceladus. And this is actually something you see a lot on the moons of Uranus and Neptune, these weird shrink wrap features, and they have these funny names like Scarps and Regiones and Solkai, which is really just astronomer jargon for we have no idea what caused them, so we're just going to give them some funny names. But there seems to be something going on where this thing has cooled down so much and shrunk so much that actually creates these very weird-looking features. Okay. So Jovian planetary systems, third part is the rings. Again, Saturn is very famous for having a ring system, but they all do. Uranian rings, Neptunian rings, the Jovian rings, we'll just put that in infrared, are there. You can see them very obviously in this. So 4 out of 4, these must be a universal feature. So what is it that's making these rings? And the current theory of ring formation is that the ring actually is kind of a self-supporting structure in the sense that once you have a debris field, the collisions in between the debris field and other parts of the debris field make it settle out into this very thin ring by some sort of grinding process. So, and if something new comes in, it gets caught by the ring system. So it's almost like the rich get richer. This is a cartoonified version of that. So let's say very early in its history, a Jovian planet had a bunch of little moons, many, many, many little moons. And then something comes in and hits one. So it creates this debris field. Well, the debris goes up, and then it comes back down. It's likely to collide with something else. So then that makes more bits. And then that stuff comes up and goes down, and as it kind of bobs up and down like a horsey on a carousel, it interacts with the rest of the stuff, and eventually a ring is formed. And the whole ring structure just kind of damps itself down. So if you want to make it through this thing, you're likely to collide with something, and it's going to stop you, and eventually you'll just settle into the ring. And this process is really, really efficient. So in the case of Saturn, the Saturn ring system is like 250,000 kilometers across. So if you want to get in a jumbo jet and fly from this end of Saturn to that end of Saturn at top speed, it would take you, provided your jumbo jet worked without air, but that's a different issue, it would take you a month. So this thing is very, very large in diameter. However, if you wanted to walk across the thickness of Saturn's rings, In some places, it's actually less than 100 meters across. So the thickness of this thing is less than a football field. So it's an incredibly efficient process that damps this thing down almost into this kind of razor's edge. And we just happen to see Saturn's rings because they're tilted towards us. But if they were edge-on, we'd never see them. And so this process is confirmed because we've actually seen Jupiter in particular actually collect some material. Didn't go into the ring system, but it definitely got ripped apart by tidal forces. So this is the comet Shoemaker-Levy 9, which was observed by 2 amateur astronomers in 1994, and it became obvious it was just headed right for Jupiter. As it got closer, the comet itself ripped into a bunch of sections, again because of Jupiter's tidal forces, and then they all impacted. And they impacted at kind of hour intervals, so Jupiter actually rolled underneath the impact, and they hit at different locations. So this is another infrared image, basically brighter, hotter. There's Io. Now you guys know why Io is burning up comparatively, because it's being heated by the tidal forces. And then these are the impacts of the bits of the comet Shoemaker-Levy 9. So this is kind of a once-in-a-million-year event. And it was just after the Hubble Space Telescope got its contact lens. In fact, people were really excited to have such good observations of comet Shoemaker-Levy 9. And I will play this partly so you can see how late 90s dated it was. Let's keep it big up. Explosions on the planet. Fragments from cubic heaving made impact. Astronomers observed 5 massive explosions on the planet. There you go.
Solar system for hundreds of years. Half an hour after the first comet fragment went in, the impact was still visible. A cloud of debris spread out for thousands of miles and was over 1,000 miles high. The astronomers were jubilant.
We're going to see things and we're going to learn a lot. That's the good news tonight.
So they were excited, not only because the Hubble Space Telescope worked, because it was so obviously a dinosaur killer. I just want to show this part of the video because this will come up in exactly one lecture. This is the path that the cometary fragments are taking towards Jupiter in this simulation, obviously not a real video. But what do you notice about the tails of the comets? So I'll show one more time. So the tails of the comets point in a different direction. And that is accurate, and we'll talk about why that is and what's going on with comet tails in the next lecture. Okay, so rings have a lot of features. You can dedicate your entire life to studying them. I'll just point some of them out because they're really pretty. They get separated into things called ringlets. They're little baby moons that live inside of the rings called gap moons. There are multiple moons that tend to kind of corral ringlets in between them. So these are called shepherd moons. And these two things, as they orbit, actually collect this strain of material between them. And roughly speaking, what the rings are made of is you can kind of think about it as like a big puffy snow cone. So you have a tendency to think about the stuff as rocks and gravel. But remember, volatiles are the story once you get out beyond the asteroid belt, main asteroid belt. This is really kind of fluffy, icy material more than anything. Okay, so how do we know this stuff? We talked about the argument for the composition of the planets. And we do send probes. We do have Earth-based telescopic observations. I showed you a little bit of infrared. That's part of this whole science called spectroscopy. But we fly by them. And this is going to be one of the last times that I can say that, is we actually directly gather evidence by sending man-made machines there. And just, it takes years to do it, in fact. So the New Horizons craft, I think, was launched in 2004, and then it made it to Jupiter on its way to Pluto 3 years later. So it takes a while and a lot of effort. And we'll talk about the story of the Voyager probes because it really is kind of a remarkable achievement. So these were launched in 1977, made it to the Jovian planets in the early 80s. Galileo went back. Cassini is actually still around Saturn, and New Horizons flew by Jupiter again on its way to Pluto.